Hello, everyone. Welcome to the webinar. Today, I'll be talking about cost-effective technologies when it comes to localizing objects that are highly reflective and complex shaped. This was part of the work we took on under the NREC program here at IMR, and we looked at various technologies to find a suitable solution for a robotic pick-and-place application. So a little bit of background about the application. There are multiple objects in a tray that are located in their individual slots, and that could be in any random orientation within those slots. So this type of arrangement comes under a semi-structured problem where it's not completely random, where the objects are in a pile overlapping each other, and it's also not a completely structured problem where everything would be in the fixed location each time, every time. So at the time, these objects and trays were manually handled for a feeding operation. There was a lot of repetitive tasks involved that could lead to ergonomic injuries. That's why it was a good opportunity to look at automating this handling process using a robot. For a successful pick and place, a vision-guided robot would require a precise 3D location of these objects. Some of the other applications where a vision-guided system can be used are bin picking, random bin picking, inspection, assembly, and packaging. In these applications, when your object is highly reflective and complex shaped, the system costs can go increase, and with that, only the vision systems costs going more than 100K. Which brings us to our challenge for this project, which was to localize this object in 3D, which would give us a 6-dimensional pose for this object. The system should be able to deal with different levels of surface finishes, from very matte, a dull surface finish, to a very highly polished reflective surface. The system should be accurate within ±3 millimeters for localization. The system cost should be within 30K euros, and the cycle time requirements from the system were less than 15 seconds. So when we think about 3D localization, the first thing that comes to mind is 3D scanning, which is analyzing real-world objects to collect data on its shape. The point data that is collected on the object contains 3-dimensional distance information. When it comes to non-contact-based 3D scanning, there are two types of techniques: active-based scanning and passive scanning. The active scanners emit light or radiation onto the surface of the object, and it detects the reflected light that is reflected from the object in order to determine distance information for that object. While the passive scanners, they don't emit any light or radiation of their own. They rely on the ambient light within the environment to determine the shape of the object. So a lot of the scanners that are available on the market are active type scanners. They're usually typically catered toward our everyday matte finish objects. Majority of them are unable to get meaningful data on reflective objects. That is because of the type of reflection that occurs when light interacts with these objects. So when light hits the matte surface, it undergoes something called diffuse reflection, where an incident light reflects in multiple different directions, and the receiver on the scanner is able to capture some information about the surface. While in reflective surfaces, they undergo specular reflection, where the incident light is reflected in equal and opposite direction, and it fails to reach the receiver of the sensor. And when the object is complex shaped, it gets more difficult. So in order to find a suitable machine vision solution for our problem, we looked at various technologies from different vendors and technology providers all over the world. And then we down selected based on our requirements from the system. So for the technology assessments, we used an orthopedic implant that was randomly placed in the semi-structured tray. We consider two surface finishes, a matte finish and a highly polished mirror-like finish for this implant. We send implants to different tech providers and vendors to capture scan data on the objects. Then we perform 3D CAD matching using Halcon to perform object recognition and pose estimation. After that, the result of the matching score from the object recognition and pose estimation were analyzed. These are the top 3 down selected technologies when it comes to scanning highly reflective objects. The first one here we have from the Euclid Labs, that this scan was captured from a motorized laser line scanning system. It was able to capture good amount of data on the reflective object and with less noise. Next up, we have a scan from the InSensor scanner from IDS. That was able to capture good data on the reflective object, but it contained a lot of noise, which would give inconsistent result in object recognition and pose estimation. Lastly, we have a scan from a deflectometry setup from Vistronics, which was able to capture good noise-free data on the reflective surface, but the amount of surface that was captured was not enough to perform a reliable pose estimation on the object. This table shows a summary of the CAD matching results from different scans that we received from different scanners. Most of them were able to capture good data on the matte finish object, and we got good object recognition scores for them. A majority of the structure light based scanners were not able to capture good data on the reflective surface object, and the CAD matching failed for these scanners. The laser line based scanner that was able to perform very well on the highly reflective object was slightly over the budget range of 30K. And lastly, the deflectometry based scanner, it captured very less amount of surface of the reflective parts, hence there was very little matching score. And then this type of system only works for highly polished mirror-like object. It doesn't work for matte finish objects. As we were unable to get a passive technology for localizing objects on the market, so we built our own in-house setup using a 2D camera with a 3D CAD matching technique using Halcon. And a universal robot was used to evaluate the alignment errors. The technique we use in Halcon was called shape-based matching. And how it works is that it places a virtual camera around the 3D CAD model of the object, and it creates a model that contains multiple 2D views of that object. And those 2D views are used to match the contours that are detected in the online image while during the object identification, recognition, and pose estimation phase. As this whole setup is calibrated, therefore we are able to get the full 3D pose of the object in the bin. So by using this setup, we were able to successfully localize the object in the bin across a variety of different orientations and variety of different surface finishes. We also tested this setup against different parameters like polarization, light color, and background color, and analyzed the average repeatability error across X, Y, and Z dimensions. The dotted line represents the 3 millimeter error threshold, and we found that the green light with a gray background and using a standard 2D camera gave us a good result across all 3 dimensions. And using a polarized camera, we got overall good repeatability and less error across different parameters. Here is a short video of the robot moving to different implants on fixed locations. The pose of the object that is found in the camera coordinate system is transformed into the robot coordinate system, so that whenever the object is in a different orientation, the robot is able to align properly with the object. So in summary of the active technologies, we found that scanning technology had the best overall results among the active technologies that we evaluated on the market. The deflectometry-based system was only suitable for mirror finish objects, and the shape complexity added complexity to the deflectometry system. The structural light-based scanners with onboard data optimization and noise reduction performed well compared to similar type of technology-based sensors on the market. And in terms of the passive technology that we evaluated, it performed well for highly polished and matte finish objects. The technology that we used was shape-based matching, which required a 3D CAD model for 3D pose estimation. And then the accuracy and repeatability of the system increased by the use of enclosure, polarization sensor, and a green light and a suitable background. So in conclusion, a passive shape-based approach or an active laser line approach are two cost-effective technologies that work well when you are locating objects that are highly reflective and complex shaped. That's all for today. Thank you very much.